All right. So we continue with small discussion in connection between minimality and Hodge theorem, meaning dependability of Hodge theorem. So it's a great pleasure to introduce Laurent Meersseman from the University of Hodge. He's going to tell us about the first number LVM.
Thank you, Randy. You hear me? Okay. Thank you for giving me the opportunity of this talk. We'll talk about non-scalar geometry, and I'm very happy to see that this topic, there is a renewed interest in this topic. So, okay, this is a joint work with Ludmil, Johnson, and Ernesto. And in fact, it is related to the flows taught by Johnson and Ernesto this afternoon. You can see my talk as a source of motivating examples for their talks. And the general idea is that Hodge numbers of non-scalar manifolds can be also interesting. Let's say it like that. Okay, the plan in two parts. First, I will give a panorama of LVM manifolds because it's not a widely known notion. And then I will focus on the Hodge numbers and especially on the combinatorial aspects of the Hodge numbers. Okay, so first a bit of history. So LVM, and there is a variant LVM manifolds. There are non-scalar manifolds introduced by Santiago Lopez de Medrano in 1997, generalized by myself in 2000, and then generalized by Frédéric Tozio. To be a bit more precise, you will see in a moment that you start with some parameters to do a construction of these manifolds. There is an important parameter which is m, which will become clear just after. Santiago and Alberto did the case n equal to 1. I did the general case m arbitrary m. And the generalization by Frédéric is a bit different. He slightly changes the construction to obtain a larger class of manifolds. So there are a few differences between LVM and LVMB. Of course, the name are coined after the acronym are coined after the names. There are a few differences between LVM and LVMB. But to simplify, I will stick on LVM manifolds. And as for the result on Hodge numbers, the second part, there are no differences. The result that I will explain for LVM manifolds are also valid for LVM. Okay, so to construct these manifolds, you need some parameters. It's actually the collection of vectors in CM, collection lambda. So you see these two parameters n and n. You need that n is strictly greater than 2n. Then you take your collection of n vectors in Cn, and you ask them to satisfy some combinatorial conditions. You want 0 to be inside the convex hull of this lambda, but not at an internal wall. So perhaps I will show you a picture that will be easier. So here, of course, I draw a picture for n equal to 1. So we are at C. So you have 5. Okay. First, I can try that. You have 5 lambdas. Here you would have lambda 1, lambda 2, lambda 3, lambda 4, lambda 5 on each case. And you see that on the left, okay, I draw, for each case, I draw the convex hull and the internal walls. So on the left, that's okay, it's admissible. You have 0 inside the convex hull, not on an internal wall. On the right, that's not admissible because 0 is inside the convex hull, but it is on an internal wall. Okay. So very easy combinatorial condition. So once you have such an admissible lambda, you define two things. First, an open set of a projective space. I didn't write down the formula for p lambda, but there is a complete formula, completely determined by lambda. And then you look at this holomorphic action of Cn. So this action, in fact, it's the composition of the flows of m linear vector fields on a projective space. So this is really a holomorphic action with exponential, etc. And you restrict this action to V lambda, and you check that the quotient of V lambda by this action is really a compact complex manifold. This is n lambda. Okay. Starting with lambda, this determines V lambda, the action, and the quotient is your manifold, or your IBM manifold n lambda, the dimension n minus 1.
What's V lambda?
Okay, V lambda, well, I can write it down. V lambda is the projectivization of the set of points N such that 0 belongs to a convex Earth of the lambda I for Ci different from 0. I mean, you take some point in Cn, you look at the non-zero coordinate of this point, you look at the corresponding collection of lambda. If 0 is in the convex Earth of this stuff, you keep this point. Then you projectivize to obtain something in the projective space. Okay, so the first result is that, okay, you have a special case when n is equal to 12 plus 1, where you obtain a complex torus. In fact, you obtain any complex torus like that. But then, in the case n strictly greater than 12 plus 1, you end up with a manifold which is not Keller. In fact, it is not symplectic and not in Fujiki class T. So in other words, it's not bimeromorphic to a Keller manifold.
Why is it compact?
Why is it compact? Because you are in a projective space, and okay, you can prove that V lambda divided by this action of Cm smooth quotient corresponds to quadratic projectivization of a quadratic. Well, of course, you have to make some computation to prove that, but you can prove that. So this lives in Cn, productive like this is compact. Okay, just a word to prove that it's not in Fujiki class
Is
T.
there just one equation?
Sorry.
One equation?
Yes, but the lambda I is something in Cn. So this is in Cn. So it gives you 2m equations of I. So to prove that it is not in Fujiki class T, what you prove is that the Hodge numbers H01 and H10 are different. Okay. So we have our class of non-Keller manifolds.
Is it clear it's a manifold?
Sorry?
It's clear that it's a manifold?
Well, in fact, the system is non-degenerate because you have weak hyperbolistic condition. You can check that easily. Okay, so for these LVM manifolds, you have two interesting type of properties. First, the topology. One of the main features of this class is that you construct example with a very complicated topology. I will come back to that. And of course, you are also interested in the complex analytic properties and the relationship between topology and complex analytic properties, since we are the non-Kähler world. So you expect something very different from what happens for Kähler manifold. There is a general principle, which is that complex analytic properties of this manifold depend on the arithmetic properties of lambda. And whereas their topological properties depend on the combinatorial type of lambda. The combinatorial type of lambda, I mean the form of the convex hull of a lambda and where zero is located, in which chamber is zero. Of course, as every principle, we will see that it's not completely correct. But let me elaborate on that. For example, if you look at the algebraic dimension of the LVM manifold, and you can, at least in the simply connected case, it's easy to compute. So you do the following. You look at the set of a fine relations between the lambda. You look at this over Q. So you look at the solutions of this system over Q. The dimension of this set of solution over Q is the algebraic dimension of n lambda. So this is what I call arithmetic properties of a lambda. Okay. In a generic case, there is no rational relation like that. So you end up with a manifold with no non-constant meromorphic function. And on the contrary, if the lambda I have all their coordinates rational, then the algebraic dimension is maximal, n minus 2, minus 1. And in that case, we can be more precise. There is a feature of the construction I didn't explain that when you do a construction with all the details, you see that from lambda, you obtain manifold n lambda. But in fact, you obtain for free that this manifold comes equipped with a holomorphic foliation of dimension n. In fact, you construct a pair manifold foliation. And this is LVM I proved with Alberto in 2004. In the rational case, so when A lambda is maximal, this foliation is a foliation by a complex array, so a foliation with compact leads. And your LVM manifold is a torus vibration over the quotient, which is a projective toric orbifold. In other words, you algebraic reduction in that case is a projective toric variety. Okay. So this foliation has many nice properties, and it is related. Let me just say a few words about that. It's related to the notion of quantum torics. I guess that Ernesto will talk about this in more detail. So let me just cite this and be very brief. In a few words, quantum torics are complex analytic stacks, but are related to irrational fans. So if you look at standard toric varieties, they are in correspondence with standard fans, standard rational fans. And here quantum torics extend this to arbitrary irrational fans. So I just draw a fan of an irrational T2. So you have 3 1 cones, 3 2 cones. It has the form of the fan of the standard T2, but it's not a fan in the usual sense, because the third vector is 1. This one is not rational. it does not contain any points of the integral lattice. So quantum torics is a way to construct analytic stacks corresponding to this type of line. Okay. I won't be more precise about that. It's a story. Okay. But there is a relationship between these quantum torics and LVM manifolds. And this is given by this natural foliation. So in fact, this natural foliation is given by a local reaction of some Cm. So recall that in the rational case, this is a foliation with compact leaves. And you take the quotient, you obtain a projective toric orbifold. Now, if you are not in the rational case, if you are in the irrational case, you still have these foliations, but now it has non-compact leaves. You still can take the quotient. And if you do that, you take the quotient at stack of n lambda by the action defining this foliation, you obtain an example of a simplicial quantum toric. Conversely, any simplicial quantum toric can be realized like that. Okay, so of course, the theory of quantum torics can be developed without any reference to LVM manifold. But there is a relationship between these two objects. Once again, LVM manifolds serve as source of examples to introduce this type of thing. If we go back to LVM manifolds, the geometric picture you have on mind is that you have a LVM manifold with its foliation. When you move the lambda a little, I will come back to that, you just deform the complex structure. And you deform also the foliation because you don't, in fact, you deform the pair complex structure foliation. When you pass, when you attain a point with rational lambda, configuration lambda with rational coordinates, this was the theorem before, you have a foliation with compact leaves and a quotient which is which is a projective toric variant in the classical sense, or at least not before. When you are in the irrational case, then you have a foliation with dense leaves, and you have as quotient one of these quantum torics. When you look at this type of deformation on the fan, you are just moving the one cones of the fan. The rational points correspond to deforming the one cone such that they are all rational, and you have a irrational case. Okay. Now let me switch to the topology of this manifold. As I told you, what is important for the topology is the convex hull of the lambda. In fact, to be a bit more precise, I already said that, but let me be a bit more precise. If you move a lambda without breaking single condition and without breaking weak hyperbolistic conditions, then an easy application of Meersseman lemma shows that you don't change the diffeomorphism type of n lambda. Okay, so if you have the same convex hull with zero staying in the same chamber combinatorially, then it's the same topology. So this is not very easy to handle, so we will transform this data of the position of zero in the convex hull by taking a gauge diagram of the convex hull. So I put the definition, but it's a bit weird for us. So you start with a convex hull of the lambda, which has n vertices, and which is in CL, so which lives in R21. You label the vertices by 1 to 1. Then this gauge diagram is a completely combinatorial transformation. So you construct another polytope, which has dimension n minus 2m minus 1, and which has at most n vertices. And there is a combinatorial rule to understand what is this polynomial, this polytope, sorry, which is that if you take a subset of one n, then this will generate a face of your gate transform, your gate diagram, if and only if 0 belongs to the convexor of the lambdas corresponding to the complementary sets. So I will give example after, but let me just explain what happens for the set of vertices. For example, if you want to know if some number j between 1 and n correspond to a vertex, well, with this equivalence, this will be the case only if 0 is in the convexor of remaining lambda I. Okay. When it is not the case, while j is not a vertex, so at the end, you have these special values which are not vertices. They correspond to some points, some lambda I that I call indispensable points. And the number of vertices is n minus the number of indispensable points. So let me give you an example. Once again, for n equal to 1 in the pentagonal case. So I draw on the left an admissible lambda. 0 is in the chamber, it's not the same chamber as before, but it's a possible choice. Here you see that the two wet vertices are indispensable because if I remove 1, 0 is no more in the convexor of the remaining lambdas. 0 is not in the convexor of 2, 3, 4, 5. In the same way, if we remove 2, 0 is not in the convexor of 1, 3, 4, 5. 2 is not a vertex of a gate transform, of a gate diagram. So finally, that tells you that in this case, the gate diagram is a triangle with vertices labeled 3, 4, 5. So take care that here it's a very special case. You start with a polygon, you end up with a polygon. But in general, the dimension is completely different. Okay. Another example, if you move 0 in this other chamber, and you just have one indispensable point, 2, and you end up with a square. That's Gantt diagram. Finally, if you put 0 in the central chamber, there is no indispensable point, so you end up with a pentagon. But observe that the labeling of the vertices of the polytope P is also given by this combinatorial law of Gantt diagram. 1, 3, for example, is an edge because if you erase 1 and 3 on the left, you see that 0 is still in the convexor of 2, 4, 5. On the contrary, if you look at 1, 2, it's not an edge, sorry. It's not an edge because if we remove 1 and 2 on the left, 0 is not in the convexor of 3, 4, 5. So you have this combinatorial yoga that relates the chambers of the convexor of lambda to the faces of the associated polytope. Okay, so we will take as combinatorial data for LVM manifolds this polytope plus the number of indispensable points. Okay, once you have that, you have a realization theorem. First of all, this polytope is always a simplicial polytope. That's easy. This is just translation of the weak hyperbolicity condition. the fact that lambda satisfies weak hyperbolicity through this gate transform stuff, that tells you that P lambda is simplified. What's more interesting is that you can realize like that any simplicial convex polytope. Starting with any simplicial convex polytope, there exists a LVM manifold and lambda whose associate polytope is exactly this P, combinatorially, of course. And you can ask this LVM manifold to be simply connected. Of course, there is not just one because it's purely topological. Once you have one, you can deform the complex structure, and in fact, you have a space of deformations of such LVM manifold. But you can also, with the same P, realize it from LVM manifolds with any number of indispensable points, like with many indispensable points. So let me be more precise to explain this statement. In fact, the simply connected case corresponds to, you can check, that corresponds to no indispensable point or one indispensable point. So when you realize two, when you prove two, depending on P, depending on the number of vertices of P of its dimension, you end up with a simply connected LVM manifold realizing P, but it may have 0 or one indispensable point, but for every P, there is just one possibility. Okay. And then there is a process, sort of stabilization process that will come back later in this talk. And when you have your simply connected LVM manifold realizing P, you can construct another one, adding 2 more indispensable points, increasing the dimension by 1, but with the same polytope. So if you start with a configuration with 0 indispensable points, you can construct some configuration with an arbitrary even number of indispensable points, but share the same associate polytope P. And if you start from a configuration with 1 indispensable point, you obtain the odd number of indispensable points. So this stabilization process, from the topological point of view, is just that you replace your n lambda with a product of n lambda by the 2 real zones. So you take the product with 2 circles. Okay. Now the topology. How can you describe the topology of this manifold? So by chance, there are many interesting properties. When you do the construction, you can check that the LVM manifold has the homotopy type of the complement of the subspace arrangement. In fact, the V lambda I just written here, you can check this is the complement of the subspace arrangement of P and minus. Also, they are diffeomorphic to the transverse intersection of real quadrics. And because of this form, they are acted on by a real torus. Quotient is a polytope. In fact, you can prove it's a dual of the polytope I introduced. So that tells you that these objects are homeomorphic to what is called moment-level complexes. Right, at least if k is equal to 1, otherwise it's a moment-level complex product with some circles or a quotient of a moment-level complexes. But okay, it's related to moment-level complexes. Now there are lots of literature on the topology of these objects. For example, de Longueville gives a topology formula for the complement of the subspace arrangement. You can use that. Santiago wrote a book and many articles on the topology of this type of intersection of quadrics. Buchstaber and Panov also wrote a book and many articles on the topology and the homology of instrumental complexes. So from that, you can derive many formulas. Let me give you the most adapted for our purpose today. Formula that I proved with Frederick in 2006. This gives you the homology groups of n lambda with coefficient in Z. We adjusted the case k equal to 1, but from that you can derive all the other cases. So the point is, everything can be read on the associated polytope. Everything is encoded in the combinatorial data of this polytope. This formula tells you that to compute the homology group of n lambda, you just have it's maybe very complicated, but you have to compute the homology groups of all the maximal subcomplexes of P. I will give you an example in a moment. Just a word with this tilde on the right, just because it's reduced homology. So I want that if Pi is contractible, does not give any class. Okay. So here you see you take the sum on all the subset of the set of vertices. Okay. Let me give you an example. If you start with a simplicial polytope like this, an octave one, and if I take the subset of vertices corresponding to the 4 vertices in red, then the maximal subcomplex we generate in the octagon is this cycle in red. Of course, this cycle has homology in dimension 1. And the formula before tells you that the Z generated by this homology is a part of the homology of the manifold n lambda in dimension 6. By the way, from this formula, you can prove that n lambda can have arbitrary amount of torsion. Because it's not difficult to show that if you start with any finite simplicial complex, you can realize it as a maximal subcomplex of some simplicial polytope. When you apply this formula, it tells you that all the torsion you have in the homology of your simplicial complex will appear in the homology of the corresponding LVM scheme. Okay. So let us switch to Hodge numbers of LVM manifold. So for that, I have to define a subclass of LVM manifold that will be, from my point of view, the most interesting one. Here, this is curious because for a long time, the idea, and I was really thinking that the most interesting example were the simply connected ones. Because, in fact, if you take a non-simply connected, from a topological point of view, you just take a simply connected one and take a product with circles, so that's not really interesting. But from a complex analytic side, there are properties I can prove only for simply connected LVM manifold. You saw one of them, the algebraic reduction. The algebraic dimension. The theorem I gave, it was when LVM is simply connected. If it is not simply connected, it's just an inequality. Okay. But for Hodge numbers, it's completely different. It's the good subclass to look at is a class of LVM manifold with many indispensable. Let us look at that class. Many indispensable point, I mean that you are at least that you have strictly more than m indispensable point. In that particular case, you have two nice properties. N lambda, we call that N lambda is defined as a quotient by a CN action of some open set of space. But in this particular case, you can rewrite n lambda as a discrete quotient. And this discrete quotient is quite simple. You can make all the computation. It's a bit okay, not very nice, but you can do all the computation. And you can check that it's the quotient of an open set of Cn minus n minus 1 by an action of Zn through diagonal matrices. One direct consequence is that this LVM manifold, when k is strictly greater than n, they are affine in the sense that you have an atlas with changes of charge given by affine transformation. When we are in this situation of at least n plus 1 indispensable point, I will say that we are in the stable range. And for this presentation, I will focus in particular on the minimally stable case, so a case where k is exactly n plus 1. Okay, it's not difficult to rewrite the realization theorem to say that given any simplicial convex polyt of P, there exists a minimally stable LVM manifold which realizes. And roughly speaking, it is unique up to deformation. Think of you can move a lambda if you don't. If zero stay in the same chamber, this also works. Okay, so now computation of the Hodge numbers. We have done it in the polygonal case. So the polygonal case, I mean that P is polygon, right? And of course, we have done it in the stable range case, but here I just will write the formula for the minimally stable case. So the parameters are n equal to L, n equal to L minus 2, and of course, this we have the minimally stable case, k is equal to n plus 1. So we obtain this formula. So some words about this formula. You see that okay, this term is only non-zero when p is equal to 0. So it gives you the HPQ for p equal to 0, and this is just a binomial coefficient. Not very interesting. On the other hand, you have these numbers here on the. This is.
Well, where does the complex structure come from? Where does the complex structure that absolute values of one of it?
But this is just a smooth model, it's infinity model. This is not. The point is that it's a complex manifold as quotient by a complex holomorphic action, but it can be realized as a smooth manifold in the projective space, but it cannot be realized as a complex submanifold in the projective space. So this model is just a smooth model.
Yeah, but what is the complex structure?
And you have
the Hodge number.
yeah. You have okay, in some open set of Pn minus 1, you have foliation, holomorphic foliation. Okay. And you can look at this smooth submanifold. Okay.
Oh, that's a
The transverse chart of the okay.
the transverse.
Exactly. Okay, so coming back to this formula, so on the left you have a Borrowing term of binomial coefficient just for p equal to 0. On the right, borrowing term which is the same by their duality, in fact, which corresponds to p equal to L. Replacing terms are in the middle. You still have this binomial coefficient, but you have this numbers CLP. So I will come back to the interpretation. That's the most interesting part. point of view. But before that, let me emphasize what you see of this formula. This is that VHPQ are purely topological numbers. It depends only on L. So we call that we are in the non-Kähler world. Of course, in the Kähler world, VHPQ are topological. But in the non-Kähler world, there are examples where they are not. In fact, normally in the non-Kähler world, when you deform the non-Kähler compact complex manifolds, the HPQ are just upper semi-continuous. But they can move. Okay.
But this formula is black.
Sorry?
This formula is black.
Yes, in fact, when I say topologically, it's always up to this infinity diffeomorphism.
No, it's just.
Yeah. Okay, so the fact that they are purely topological is really something perhaps not unexpected, but something which is not evident at all. Okay, so before analyzing this with more care, let me give some remarks about the proof of that and about some related results. There are some special cases, some special rational cases where when n lambda is a torus bundle over a smooth projective Turing variant. In that case, you can prove this type of formula by using the wide spectral sequence. And in fact, there are many results about that. You have especially a paper by Hodge, which proves that for wide spectral sequence for torus bundle degenerates at age 3. Then you have a paper by Paddock and Justinovsky, which applies that for LVM manifolds with k equal to 1.
What is USC?
The semi-continuous.
What?
The semi-continuous.
What?
The semi-continuous.
What's the first word?
Well, sorry, my English.
Fair.
Sorry.
Fair.
Okay.
Fair.
Unfortunately, you cannot prove this theorem like that because you expect, a priori, you expect this HPQ to jump at some point. Okay. And there are only special points where you have really a torus bundle. Of course, so in the theorem, you really have to think that we prove the formula and then we observe what is topological. It's not the other way around. The general case, there is also a nice paper of Kuntowski and Panov that gives a model for the Dolbeault homology of L lambda. It relates it to the basic Dolbeault complex of holomorphic foliation. But this type of result is not precise enough to allow you to compute Hodge numbers. So finally, we follow a more basic approach, which is in fact very strategy to compute the homology evaluated in the tangent sheaf of the Hodge surface. You look at the universal covering of the LVM manifold. This is a special type of open set of an affine space. You compute its cohomology. You realize the cohomology classes have some special type of power series. Then you compute the invariant terms. And then you using a Stein covering on L lambda that you pull back to the universal covering. You relate the cohomology groups of N to the subset of invariant terms of power series. So strategy is quite clear. It's complicated because combinatorics is a bit complicated, and it's why it's just done in a polygonal case. Of course, it's much easier in a polygonal case. Okay. So let us see an example of Hodge diamond. Once again, the pentagonal case. So here, since we are in the minimally stable case, I don't have n equal to 1, but I have to shift to n equal to 3. So first you have this boring term gives you p equals 0. So, okay, my notation, when you go on the right, q is increasing. When you go on the left, p is increasing. Of course, here it will not be symmetric, so there's a choice to do. So this is the MQ that appears, M is equal to 3. So that appears for the Hodge number for P equal to 0. Then you have a symmetric term for P equal to 5. Then you have a famous CLP. Here you just have two of them. You compute they are equal to 5. You have a bunch of 0 among them. And then you complete your Hodge diamond by multiplying with always the same binomial coefficient. So you will appear, you see that appear 5, 15, 15. So of course, in non-Keller, you can see the bottom as the first Hodge number as 0, 1, and as 1, 0 are 0 and 3, so symmetric. You have, of course, their duality. But then everything is computed from these two numbers, from these numbers CLP. Your numbers are okay. Do this, okay. So let us try to understand what are these
Is it always intentionally symmetric?
Yes, this is given by duality.
Yes.
Yes. So H n minus p n minus q is the same as h p q.
Okay, that's
Okay, so
that's not true for any compact complex manifold.
yes,
Any compact.
yeah, any compact manifold. Okay, so let us try to understand this CLP. So from the proof, since really you enter into the details of the combinatories, you can see what happens. It's easy to see that CL2 is just the number of pairs of non-adjacent vertices in your polygon. And for the others, then you can prove with a little more care that CLP, given as follows. If you look at the subset of vertices of length P, of P vertices, you look at the maximal subcomplex degenerate in the polygon. You obtain something which is just a bunch of edges and isolated vertices without the autopy of a finite set of points. And you just compute reduced zero Betti number, which is just you compute the number of points minus 1. So of course, I wrote this in this rather complicated way. We call you the topology formula I gave before. It's the same style of formula because everything is at the end depends on the maximal subcomplexes of your polygon. Okay, so from that we can have a second interpretation of CL lambda. If you look at the topology of these manifolds N for the polygonal case, well, they are diffeomorphic to some simply connected part XL times the many circles. That's normal. We are in the minimally stable case, so we have to deduct with circles. XL is one of the moment-able complexes. In fact, it's a smooth manifold of dimension L plus 2 with an action of the N torus, and with caution given by manifolds. And the topology of these objects is well known since work by Maguire in 79. Well, I should add also contribution of Santiago, but I'm not sure what's in the original article. It's really, I think it's one the PL case. In fact, it's diffeomorphic. So this part itself is diffeomorphic to this connected sum of product of spheres. Okay, so what's the point? Well, from the formula before, we saw that our Hodge numbers are related to the topology formula. In fact, we can be more precise. We can just check that the CLP is exactly the Betti number of degree p plus 1 of xm. So just checking. But there is more. You can check now easily that, in fact, the polygonal minimally stable LVM manifold satisfies Hodge decomposition. So of course, it's not canonical Hodge decomposition, it's just you check, you have a formula for the HPQ, you have a formula for the Betti numbers of XL, so you have one for the Betti numbers of N. You just write down the, and you check that they satisfy Hodge decomposition. So we call that they are non-Keller, they are non-binomorphic to any Keller manifold. So by accident,
You mean this Delbo spectral sequence collapses?
it collapses, but not.
What?
Yes, it collapses, but I don't remember at page 3 or something like that. It's not Keller, so it is.
But page 2 is the Hodge numbers. So how can you have Hodge? It's ordinary homology
You have.
is the sum of certain Hodge numbers.
No, it's really, you can check that you have BK. So,
Then the spectral sequence collapses.
well, it collapses, I don't remember exactly
Yes,
when,
collapse.
but it's not Keller. Okay. Yes, okay, I agree, okay. It has to collapse at some point, okay, what? But that, again, the important point is that you don't have you don't have a canonical decomposition, you don't have equality of the Laplacian and stuff like that. Okay, but okay. In any case, you have a decomposition, and you can prove something more. In fact, you have a decomposition if and only if you are in the stable range. Well, it's easy to see that it works in the minimally stable case, but in fact, then it works in all the stable range. But it does not work in the unstable range. So there's something very mysterious to me. If you start with a simply connected LVM manifold, it will not satisfy Hodge decomposition, never. Especially, you look at V1 is 0, and H10 plus H01 is equal to N. That's different. But then you do this stabilization process that you add indispensable points, so topologically you take a product with circles. At some point, you end up with LVM manifolds fulfilling Hodge decomposition. And this is exactly why when you enter in the stable range. Okay. So just to finish, let me say some words about the general case. Here we just have a conjecture. The first part is not really a surprise. We hope that we have the same stabilization process. But when you add sufficiently many indispensable points, you have Hodge decomposition. So you have a decomposition even if you are in a stable range. And then a complete formula for the HPQ. So I wrote it down for minimally stable, but then you can have it for every LVM manifold in the stable range. It's more complicated. So just to comment a bit on this formula, you still see these binomial coefficients. Here you start with polytope P with dimension D and n vertices. The n minus D, in fact, it's n. So you still have this n q minus I binomial coefficient that we had in the polygonal case. In the polygonal case, we have 3 of them, okay, corresponding to 0, 1, and 2, of course, for the polygon. Here we have D plus 1. This we have a polytope of dimension D. And then what replaces the CMP, some Betti numbers of simplicial subcomplexes of P. So we have to prove this in the future. And of course, this formula satisfied, okay, if you do the sum of the HPQ, you exactly obtain the Betti number of the LVM manifold given by the topology formula, okay? But that is reasonable to have this formula. Okay, I think I will stop here.